I always start, I was looking at some old videos, I always start like this. That's what I'm going to do. Damped harmonic motion. So this is part of my mathematical method for physics course, and we're doing differential equations right now. So I think this is a good example of solving a differential equation with initial conditions. So let's get to it. So we have a mass on a spring right here, and I dropped my eraser, picked it up, and there's two forces acting on it. There's a restoring force from the spring, negative kx, but there's also a drag force that's proportional to the velocity, negative b x dot, where x dot's the velocity. We can write Newton's second law as mx double dot equals negative kx minus b x dot. And that's the differential equation that we want to solve, so let's get to it. I'm going to do two things. I'm going to divide both sides by m and move all the terms to the same side. So I have, because this is not something that you can just like, hey, I'm going to guess a solution, right? Because if I pick x equals a cosine omega t, well, I got that x dot term in there, so it's not going to work. Just letting you know. You could try it, but x double dot plus, I'm going to put the next term right here, b over m x dot plus k over m x equals 0. Now, and if you have not solved differential equations before, you should know that there's just a bunch of tricks. And once you know the tricks, things make sense. But before you know the tricks, it's like, wait, what's that? Okay, so I'm going to use a couple tricks. It's not a big deal. But at the end, we'll have a solution that we'll be happy with. And I'm going to do Python at the end too. So here's the first trick. I'm going to call this parameter right here b over m. I'm going to put it over here. B over m is 2 beta. And then k over m, we know that for a simple harmonic oscillator without friction, the angular frequency, the frequency of oscillation, is the square root of k over m. So I'm going to call this omega naught squared. So k over m is omega naught squared, where omega naught would be an undamped oscillator. We'll come back to that in a little bit. So now I have this, x double dot plus 2 beta x dot plus omega naught squared x is 0. And again, why would you do 2? That doesn't make sense. And you don't have to do 2. If you don't do 2, things just don't turn out as nice at the end. So I did 2 because I want things to turn out nice. Now, it's still a really difficult differential equation, but we can define the operator d as the derivative with respect to time. If I do that, this equation becomes d squared, the second derivative of x, plus 2 beta dx plus omega naught squared x equals 0. But see, now I have these x terms in there, and I can factor that out. So I have d squared plus 2 beta d plus omega naught squared operating on x is equal to 0. It's a trick. Okay, it's a trick. But if I want to solve this problem, I could say, well, x is 0. That's the solution. Or I could say this operator, in a sense, is 0. And if that's the case, I could actually factor out this into, I have a quadratic equation there, d squared d constant. So I could factor that into d minus r1 d minus r2 x equals 0. So r1 and r2 are just constants, but they have to exist, right? Because if this is a constant times that operator d, and that's a constant, then these should be constants. So I have two options. This operator could be 0, or this operator could be 0, operating on x, right? So we kind of break the problem from a second-order differential equation into two first-order differential equations, and that's kind of cool. Okay, so now let's find these values of r1 and r2. If I have this operator right here, and let me put it up here, I'm going to erase x, just give some more room. So I have this, d squared plus 2 beta d plus omega naught squared x equals 0. So I can use the quadratic equation to find r1 and r2. So remember that here I'm going to say a is equal to 1, b, that's a beta, is 2 beta, c is omega naught squared. So r1 is going to be the quadratic equation. negative b, so that's this, negative 2 beta, plus or minus, I'm going to go with the plus one first, so plus the square root of b squared, which is 4 beta squared, minus 4 times a, which is 1, times c, which is omega naught squared. All of that divided by 2a, which is just 2. And then R2 is going to be the same thing, except I have a minus sign there. Minus 2 beta minus the square root of 4 beta squared minus 4a AC, omega naught squared over 2. And you can see here that I have a 4 and a 4 I can factor out. And so that becomes a 2. Then I have a 2, 2, 2, cancel. 2, 2, 2, cancel. And that's why we picked 2 beta, right? Just so we don't have a fraction. If you didn't have 2 beta there, you just have beta squared, and you couldn't factor out the 4, so it'd look a little bit weird. You could do a bunch of other tricks. But in the end, I get R1 is negative beta plus the square root of beta squared minus omega naught squared. And that looks nice. And this is negative beta minus the square root of beta squared minus omega naught squared. And that looks nice. So now I have R1 and R2. Now I can go back, right? And I want to find this. I want to say d minus R1 operated on x is equal to 0. Well, that's the derivative with respect to time. So this is actually just the derivative with respect to time, which would be x dot, right, because I'm operating it on x dot minus R1x is 0, or x dot equals R1x. Now that I can solve. That is so easy that I can solve it, right? What function of x can I take the derivative of and get the same thing back with a constant? Well, the solution to that would be x as a function of time would be some constant c1 e to the r1t. Right? Because if I take the derivative of this, I get r1 times c1 e to the r1t, which is x. So that's my solution. Now, if I go over here and do d minus r2, I'm going to get the same thing, except I get x as a function of t is c2 e to the r2t. And remember, I have r1 and r2. Well, if each of those are a solution, then the sum of those must also be a solution. So now I have my solution. I know you think, wow, that was actually kind of easy. And it wasn't too bad, right? I'm going to leave my r1 and r2 there, just so I have them. So I get x is a function of t is going to be equal to c1 e to the r1. And I'm going to go ahead and put this up here. Negative beta plus the square root of beta squared, that's a squared, minus omega naught squared, all of that times t. It's a little messy, I know. Plus c2 e to the negative beta minus the square root of beta squared minus omega naught squared t. Now, I can actually simplify this some. And so the solution here depends on, my value of beta, to tell you the truth, because it's going to determine what happens on that square root in there. Let's look at the case where, well, let me go ahead. I can write this as e to the negative beta t times e to the square root of beta squared minus omega naught squared t. So and then that same thing over there. So I can actually factor that out, and I get e to the negative beta t times c1 e to the negative, this plus, e to the square root of beta squared minus omega naught squared t plus c2 e to the square root of beta squared minus omega naught squared t. That's minus. Okay, again, what happens? Let's look at the first case, where beta squared is greater than omega naught squared. If that's the case, then this term is just an exponential. This term is an exponential. And in fact, we could write it up here, right? I have two exponentially decaying terms. So what's going to happen here is it's just going to be it's not even going to oscillate. It's just going to go, if I displace it some amount, it's just going to die down. Now, let's go ahead and model that one. I'm going to model this, which is called overdamped motion. Okay, so I'm going to switch to Python, and then we'll come back and do critically damped and what's the other one? Underdamped. Okay, so let's just go ahead and find the values for C1 and C2. So let's say that at t equals 0, x of 0 is x0, x dot of 0 is 0. So I'm going to pull it off to the side and release it from rest. If that's the case, I can write this, putting in t equals 0, I just get this whole thing to the 0, right? So that's 1. So I get C1, and this whole thing is going to be plus C2. So I have C1 plus C2 is equal to x0. So that's two constants for a second order differential equation. Now, if I want to plug in, find another relationship, I can take the derivative up here. So let's say x dot as a function of t is going to be equal to this whole thing. So it's C1 times negative beta plus the square root of beta squared plus omega naught squared times e to the negative stuff. I'll just put stuff. I don't really care about that because I'm going to put in t equals 0. And then over here I have plus C2, and then I have the same thing, almost the same thing, negative beta minus the square root of beta squared minus omega naught squared, and then I have e to the stuff, which is going to go to 0. So now if I plug in x dot of 0, I get, that's 1, so I get C1, and now I'm going to get C1 times, okay, things are getting sort of complicated, so I'm going to tell you a secret right here. If I pick this is equal to C1 is equal to x0 over 2, C2 is x0 over 2, I think it works, okay, because there's a bunch of mess stuff here. The key, though, is that, and this is the same thing, it took me a while to figure this out, you can use initial conditions at t equals 0. If you release the velocity from rest, then it's essentially as though beta is 0, because it's not moving, so there is no drag term. So in that case, this solution will work. I know that's a cheat, but I want to jump into Python really quick and model this. Okay, just a quick reminder how we're going to model this in Python. I think it's okay to reset. So in Python, what I can do is to do this numerically, right? I can say x double dot is negative b over m x minus, no, that's k over m. No, that's b over m x dot minus k over m x. I can calculate the second derivative explicitly. And then if I choose delta t of 0.001 seconds, during that time interval, I can assume that's constant. So x double dot is delta x dot over delta t, which would be x2 dot minus x1 dot over delta t. So this is the velocity at the end of the time interval. That's the velocity at the beginning of the time interval. So if I know the velocity at the beginning of the time interval, I can find it at the end after I calculate x double dot. x2 dot, x1 dot, plus x double dot delta t. Now I can do the same thing with velocity. I can say x dot is delta x delta t. So I get x2 is x1 plus x dot delta t. And then I just do the whole thing over and over again. But you need initial values for x and x dot, and you need numbers, right? I need the value for b, I need the value for m, I need the value for k, I need all of that stuff. So I'm going to say over here, let's say b is, actually I want, okay, here we need to, I'm going to say k is equal to 5, m is equal to 0.05, omega naught squared is going to be equal to k over m, like I said, so I can calculate that. And then I want beta, let's say beta squared, or beta is equal to 1.5 omega naught, right? And then I can use that to calculate b. So that's what I'm going to do. So b up here, b is equal to 2 beta m. So I'm going to set all my values and calculate b that way. Let's jump over to Python and do this thing. WebV Python, I'm going to give you the code. You know I give you the code. I always give you the code, so stop complaining about the code. Okay, you're not complaining, I know that. Let's go ahead and make a graph. Graph x title equals time, and the y title is x. And then I'm going to give it a width, 400, height, 200. Now I'm actually going to have two graphs. So let's just make two graphs. F1 is G curve, color equals color.blue. And then that's going to be my numerical calculation. And then I'm going to plot the theoretical calculation too. F2 equals G curve, color equals color.red. Now I need my constants. M equals 0.05, K equals 5. And then B, let's go ahead and write omega 0 squared is K over M. So I need that. And then beta, which I'm going to call capital B, is just going to be 1.5 times omega 0,2. That's what I just said, right? Yeah. And now I can use that to calculate B. So B is equal to 2 beta M. 2 times B times M. Now I need T is 0. dt is 0.01. 0.001. X equals 0.01. I need to have it initially displaced, and then x dot is equal to 0. Okay, while t is less than, let's just do 3. Rate 1,000. So I'm going to actually animate this in real time. Let's go ahead and put a dot here. Dot equals true. That'll make it cool. So the first thing to do is to calculate the acceleration. X double dot is equal to negative b times x dot divided by m minus k times x divided by m. Now I can update x dot. X dot equals x dot plus x double dot times dt. X equals x plus x dot times dt. And then I can update time. T equals t plus dt. And let's go ahead and plot it. F1 dot plot tx. Let's see what happens. Okay, so that looks like exponential decay right there. Okay, let's go ahead and calculate C1, C2, and plot the theoretical version too. I said I'm going to call x0 is equal to 0.01. C1 is equal to x0 over 2. C2 is equal to x0 over 2. Now, my theoretical solution, I already have my, in terms of betas, right? I'm going to just use this term up here, this first one. So I'm going to calculate that down here in one fell swoop. I'm going to call it xt for theoretical. It's going to be equal to C1 times exponent negative beta plus the square root of beta squared minus omega naught squared, which is just omega 0,2. Omega 0,02 is omega naught squared. Yep, that's that term right there. And then I need to multiply that by t. Okay, actually, this whole thing multiplied by t. Right. And then I have the same thing, plus C2. So I'm going to copy this whole thing because I don't want to type it. C2, and the only difference here, this is a minus. Okay, and now let's plot that. F2 dot plot t x t. Kind of scared, but you know, let's just do it anyway. No, that didn't work. Why didn't that work? Negative beta exponent times t plus square root beta squared. Okay, that's your homework. I want to go ahead and skip over to the underdamped equation, and then you can play around with all the values as much as you want, and it should be fine. So let's jump back to the board and write out the underdamped equation. And I apologize for that, but sometimes we just make mistakes, and if I go back and fix it the whole time, it's just going to be a disaster. My numerical calculation is fine though. It doesn't really matter what the initial conditions are. But let's say that beta is less than omega naught. In that case, beta squared is going to be less than omega naught squared, so this is going to be a negative number in the square root, so it's going to be an imaginary number. So I can define omega as equal to the square root of omega naught squared minus beta squared. In that case, the square root of beta squared minus omega naught squared would be I omega. So now I can rewrite my thing up here as x as a function of t is e to the negative beta t times c1 e to the I omega t plus c2. C2 e to the negative I omega t. And hopefully you see that this is the equation for a simple harmonic oscillator. That's the exponential form of a simple harmonic oscillator. And if I release it from rest, I can write this as e to the negative beta t times a cosine omega t. And there's no phi in there because I released it from rest. And then if I apply my initial conditions just like I did before, then a would be x0. So this is really cool because it shows an oscillating term and an exponentially decaying amplitude. And we can model this pretty easily, right? So I'm going to go back up here and let's say beta is now less than that. So let's say beta is 0.1 omega naught squared. I just picked. And then they'll recalculate everything, and then I can plot. This is my theoretical. So let's just first do the numerical calculation. I'm just going to change my values, and it should work just fine. So up here, I'm going to say beta is, I said that was 0. Oh, I see where I made my mistake. Beta is, that's beta squared. This should be square root. Let's just see if that works, because if that does, beta is the square root of omega naught squared. I think that, no, it still didn't work, but it looks better. Okay, so b is 2 beta, that's right. Square root, okay, let's put that oh, I think I had to take the square root inside of that. Is that correct? Let's do it the other way around. Let's say b is, what did I do before? B is 0.1. And then I'm going to define beta. That'll be easier. Because I think my problem was that I had the square root in there. So beta is equal to 2, no, it's b divided by 2 times m. Right? Because 2 beta is b over m. Right, got it. Okay. So now I have that. Let's just comment out F2 right here, and let's just see if we do indeed get an oscillation. So this is just a numerical calculation. That looks good, right? It's underdamped and it's decreasing amplitude. Now let's just see if our theoretical thing agrees with that. I'm going to go down here and calculate this. Let's just comment that out so you can have it. xt is going to be exponent negative b times t times x0 times cosine omega times t. Now I didn't calculate omega, so let's do that up here. Omega is equal to the square root of, what did I say it was? It's going to be omega naught squared minus b beta squared. So omega 0, 2 minus b beta squared. And that's my omega, and that goes down there. And then let's plot that. If this works, I'll be very happy. But sometimes things happen. There we go. Check that out. Those two graphs are right on top of each other. They agree with each other. So there you go. That is damped harmonic oscillation. You can play around with initial conditions, but I'll warn you, don't put the initial velocity as non-zero because things get really messy. The key here is if you put the velocity as 0, the initial velocity is 0, then there's no drag, right? Because it's not moving. And so you can make it a lot easier. You can do the other cases for overdamped and underdamped by changing the parameters, but I'm not going to plot those. That's your homework. Hope you enjoyed that. I'll talk to you later. Code down below later. Bye. I already said that.